The previous chapter has described about the linear least square framework to estimate the model in a linear regression form given by this equation. Beta is a coefficient, regression coefficient, X is a regressor matrix, and Y is a response variable. In this chapter, we would like to extend the problem of minimizing the true norm, okay, of the error, the error that comes from the linear regression model. We would like to extend into several ways. The first one is a problem where the least square could have the constraints on beta. Beta has to satisfy some conditions, non-negative, and other things. In the second group is a problem where you would like to add some penalties on beta. The function that we add is based on the 2 norm and the 1 norm regularization terms. So these are introduced so that some desirable properties of beta are preferred, are desired. L1 regularization is commonly referred to a lasso problem in literature, and now it has even variations of this generalization in L1 sense. Group lasso, fused lasso, sparse PCA, sparse SVM. These are terms we hear all the times in the field of statistical learning. So we would like to give some short examples, some brief examples on that. And at the last group, we talk about robust least square. This is a problem when problem parameter in the linear regression, which is x and y here, the regressor matrix and the response vector y may have some uncertainty. We could model it as random, and then we provide a way to handle those uncertainty. In order to talk about this, as we will see that all the problems in this chapter will be formulated as an optimization problem. So in order to do so, I would like to change the notation a little bit in this chapter. We would use the regression coefficient instead of beta. We will use x, and we change the regressor matrix into a matrix A. Okay. We change it so that now the variable would be x, and that will be common to when we see an optimization that explain these formulations, so that it common to another source of materials like optimization textbook. We use this notation because it agrees with most of the materials in statistics that usually the regressor matrix X contain the input variable. So that's why they use the variable X here. Okay. The tools required by, for example, optimization, the tools to actually numerically solve the solution will be supplementarily provided in another video. Okay. So now let's first talk about least square with constraints. Okay. So the problem is extended in this way. The least square framework is an unconstrained problem. You just want to minimize the 2 norm of the residue. But now sometimes you have conditions on x, so we use the notation that how about imposing the constraint that x must belong to some set C. Okay, set C. This set, as you will see, in most of engineering problems, we can see that C is a convex set. A convex set is a set where whenever you find a convex combination between any 2 points in the set, the point Z is called a convex combination. If the point Z is also in the set C for any x and y in the set C, Okay, if that condition hold, we say that the set is convex. Okay. We will talk about this later when we provide the background for you, but let me mention that most of the set that we see here are convex sets. So why do we impose the constraint that set X belong to the set C? Because sometimes the reason why you use the linear model here is based on some assumption, is based on some approximation, and in order for the justification that you use the linear model to be valid, you also would like to restrict that X contain to some X contain in some feasible set. Okay. Um, when we take a look at this formulation, now we will use optimization point of view that now it becomes a constraint optimization problem. Okay. Typically, there will be no analytical solution because it depends on the feasible set, all right? And it's going to be more complicated if you would like to interpret the result because the set C is typically, I mean, in order to interpret it, it would depend on the set C. Now let's take a look at more concrete examples. First, non-negative constraints on the variables. Here, if your variable X represents some physical quantities like power, rates, price, what else? The size of some objects like width or height. Of course, these quantities are supposed to be non-negative, right? So you want to put these constraints. We use the inequality constraint like this to say that it means that all the entry of xi are non-negative quantities. Okay, but in terms of vector representation, we just use this. Okay. The set C here has a name. It's called non-negative. Sorry, it's called non-negative orthen. Non-negative orthen. Okay, so it's given by these whole, first quadrant of R1 of Rn. Okay. So finding the projection on Y. Okay, initially when we have the least square problem, we say that the least square as unconstrained problem, the Y hat obtained from the least square solution is a projection of Y onto the range space of X. But now, if all entries of X are non-negative, the interpretation is that it's a projection of Y onto the cone generated by columns of A. The cone is a positive combination, so the cone here, it means it's a set of alpha 1, A1, alpha 2, A2, alpha n, AN, where all the alpha k are non-negative. This matrix A has n columns. Okay. Why its interpretation is given by this? Because your y hat is A times x hat, right? But because you impose x hat to be non-negative, so it means x hat 1 A1 plus x hat n AN. So we can interpret your y hat as a linear combination of all columns, but those linear combinations are given by non-negative weights. So geometrically, it's represented by a cone. In the second example, if your variable x contains in an interval. Okay, now we use the vector notation again, but what would we mean is that your L is a vector y1 dot dot yn. Okay, your x is x1 dot dot xn, and the upper bound is given by the vector u. So each entry has its own lower bound and upper bound. Geometrically, this is called a box constraint. So what the graph that I see represent here is a plane of x1 and x2. All right, so this is L1, U1, this is L2, U2. So you impose your estimate, your coefficient to lies in this box. Okay, and so the interpretation is that your y hat is going to be projection onto the image of the box under linear mapping induced by A. Okay. Now let's see another example. Now this is something related to probability, related to fractions. Okay, here's the constraint. You not only want x to be non-negative, but you want the sum of all x. This is the all one vectors. So 1 transpose x is going to be x1 dot 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 plus xn. You want it to be exactly equal to 1. So you would think of x, the meaning of x, as a portion, as a fraction of quantities. For example, if x1 and xn represent the PMF of some discrete random variable, the probability mass function. So your xn, like for example, it must be 0.1, 0.2, 0.4, and then the last one must be what, 0.3. All right, it's a fraction. It's a probability. It could also represent the fractions. Like x is a portion. You want to invest the money into different assets. I want to invest 10% on the stock A, invest 20% on stock B, and so on. Okay. Now this set when you mathematically represented by this is called probability simplex. Okay, so for R2 it's going to be like x1 x2 are non-negative and x1 plus x2 equals 1, right? So geometrically is going to be given by this region, sorry, this set is on the line, and the term we use in statistics is it's called probability simplex. So your solution must lie on this blue line. Okay. So the interpretation of your y hat, again, your y hat is your y hat is what, ax hat, right? So it's going to be x hat 1 a1 dot 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 x hat n a n. But now in this with this constraint, your x1 x hat 1 and x hat n are sum up to what? Are sum up to 1. So the meaning is that your y hat is going to be convex combination of columns in A. Because if you have weighted sum like this, and if all the weights are sum up to 1, this is called a convex combination. Last one, okay, last one. You have a norm-ball constraints. Now you want, okay, given x naught and d, okay, in R2 plane, Rn plane, your x naught is some center. You want your x to lies within this area. This is a norm ball because you measure, okay, let me just put an example, the two norm. You want x to be within the neighborhood of x naught, measured by the radius d. If you use the two norm, it's going to be two norm ball. Okay, so the interpretation is the following. Your x naught is the center of this region, so it could also mean a prior guess of what x should be. Okay, and then but you allow x to lie within this area, so you allow the proximity of x to be d is a maximum possible deviation of your of your x from the prior guess x naught. Okay. In we can this representation will be denoted as a trust region. It's a region that you trust your x hat to lie within. Okay. You can also interpret in the sense that whenever you make a linear approximation y equals ax, so that you use the linear least square framework, such approximation is only valid when your x lies in this norm-ball constraint. Okay, so norm-ball constraint, if you use two norm, it looks like a it's a circle in a flat in a R2 in Rn, so it's going to be a sphere. Okay. You use other norm, geometrically the number of other norm like L1, L-infinity will have different shapes. Okay. So in conclusion, these are just examples that I gave that, okay, most engineering examples can be, you can pose the constraint on the set C in several ways. And what they have in common in this example is that these sets are convex. Okay, so we will see that, okay, your cost objective is convex function in x because it's is quadratic in x, and you have the constraint set that is also convex. So with such assumption on the feasible set C, the whole problem is a convex optimization, and numerical solution can be obtained using existing software and solvers, which means it's going to be trivial to obtain numerical solutions. So, and that will be explained in the next video clip.